Good morning. Thank you for coming to my talk. This is actually my first time ever doing a talk, and actually my first time in Europe as well. And today I'm going to be talking to you about how to abuse hardware to bypass software security checks. So I'm Brett Giller. I've been a security consultant for about almost 2 years now, and I have an interest in hardware attacks and hardware security. So for today, we're going to be going over these topics. So I'm going to start off by going over at a very high level what electrical glitching attacks are and where they can be used. And I'm going to quickly go over the reset glitch hack on the Xbox 360. And from this attack, we're going to develop a methodology to go use our on more generalized devices, as we will see up ahead. And then towards the end, we're going to look at the devices I had in mind to go over and try to attack, and ideas for glitching experiments in the future, and finally, defenses that embedded vendors can try to do to defend themselves against these types of attacks. So to start off, we should ask, what is a glitching attack? And a glitching attack is an intentional fault introduced to a device to undermine its security. And the effects of these faults can include certain actions such as instruction skipping, malformed data reads or writes, instruction decoding errors, as well as any sort of computational errors introduced into a device when this happens. And glitching attacks come in 3 flavors. They come in invasive and semi-invasive and non-invasive. And with invasive and semi-invasive attacks, we are required to perform some sort of modifications to the packaging on an IC. And this oftentimes requires a lot of time and some fairly expensive equipment. Whereas with non-invasive attacks, we don't really have to do much modification to the target device, and this could be done on the cheap. These also are quite simple to implement, as we will see later on in the talk. So with non-invasive types of attacks that we can do electrical glitching attacks, thermal or radiation attacks, and the scope of this talk is only going to really cover the electrical attacks, which include the clock and power glitching variants. So with a clock glitching attack, we introduce unplanned clock edges into the target IC, and we can use different types of glitch signals when we are doing this type of attack. So if we look at the Glitching for Noobs talk, there was one that Exide used was the 3-phase XOR signal, where he took the same clock signal and XORed it against itself with a phase shift of 0, 45, and 90 degrees. And another one would be to just simply directly flip over the clock signal for a set duration. And this actually worked for me in the Arduino example that is going to be covered up ahead. Another thing that was suggested to me was to use the increased clock speed to simply double the clock rate supplied to the device. And this I didn't really have much success with, unfortunately. So with power glitching attacks, we can do either a brownout or a voltage spiking attack. And with a brownout attack, we cause propagation delays within the IC to exist. And when we do this, it tends to be a bit more predictable, at least in my experience when I was doing it on the Arduino chip. And it's more likely the cause of write back to fail when you're doing an attack like this. So something else I tried was to do the voltage spiking attack, which these are simple to implement, but because you're effectively introducing floating signals into the target device, you it's significantly more unpredictable with what exactly you're going to get. And it's also very easy to damage the device if you don't listen to the ratings on the chip. So these are some of the typical targets for glitching. These are pretty much in any sort of scenarios where you have some sort of service that you want to steal or add on to the device. And in terms of code, you really are you want to really target branches and comparisons, really, or anything that really has a write back phase in terms of an instruction. Something you also target are memory reads and writes, which can yield some certain interesting results depending on what you do. So now we're going to go over the reset glitch hack that was done by Gleegly. And this is really similar to a clock glitching attack. And I say this because it gets effectively the same effect theorized by a clock glitching attack, which is you're skipping over an instruction when you're trying to do this type of attack. And it's considered a non-patchable exploit, though Microsoft did take steps to mitigate themselves against this type of attack. And I'm only going to be talking about the exploit on the original Xbox 360. If you look near the end of the presentation, there are links to the full write-up by Gleegly, which also covers the Xbox Slim. So before we could go any further, I have to talk a bit more about the Xbox 360's bootloader security. And this works by having a chain of bootloaders, which starting with ROM, it loads in a chain of self-verifying bootloaders in NAND. So without really going into too much detail, this code is RSA signed, and we also have the nice information being leaked out by the Xbox itself. So the exploit consists of really three main components, I would say, which is one, the CPU PLL bypass, the reset behavior, and the post bus, which emits out signals indicating to what is being executed within the Xbox 360. So the CPU PLL bypass, when asserted, slows down the processor to 520 kilohertz. And this allows for significantly easier timing when we're trying to actually implement the attack out on the device. Now, the reset is really at the core of the attack. And what happens here is when you assert the reset pin on the CPU, instead of flushing out all the volatile information within the device, it has behavior similar. Effectively, it skips instructions that's being executed on the Xbox. And finally, we have the post bus, which is an 8-bit diagnostic bus, which allows us to have insight to what code is being executed within the device when we are trying to perform a glitching attack on this. So it sends out a hex 36 signal on the bus when we are decrypting the NAND, and then we send out a hex 39 when we are performing a check on the signature. So the exploit targets the RSA signature comparison on the Xbox 360's hash, and we use the post-bus signals in order to know when to actually do so. So something else I also wanted to note was that the payload itself is set up in a way so it resets when it fails. And this indicates to us that even though we have effectively an idealized version of a glitching attack, it's not as reliable as we find out. So pretty much the steps to doing a reset glitch attack are as follows. So one, you upload the payload to the NAND using a JTAG interface. Then you monitor for a post signal using your FPGA to indicate when it's doing the decryption of the base kernel. So then from here, we assert the CPU PLL bypass. So we have an idea, so we're able to catch when the signal of the hash comparison is happening. And then we start an internal counter once we hit post code 39, which we can then, at about 62% of its normally executed length, we send out a reset signal for 100 nanoseconds. And then after all of this, we go back to normal execution. So Microsoft's response to this was to blow out the JTAG fuses, add an additional check, and then begin banning users with modded Xboxes from Xbox Live. Now, with the response from the Xbox hackers was to make use of a new exploit, which just completely bypasses the secondary check that they had, showing that if you just add on additional checks to the device, it actually won't really do you much good. So this is pretty much what we have for our exploit. It's very, very linear in nature, just because of how all the nice things that we get from the Xbox itself. So this is really because of the post signals that we get, which allows us to have a much more narrowed exploit. So from here, we try to develop a general methodology to develop attacks on other devices. So this is not really in any real steps, but it generally helps out if you have actual access to the disassembly of the code that you're targeting. Then you also need to review the datasheet to make sure that you actually can perform a glitching attack on the device. Then you want to if possible, you should try to test out the target manually. Then you try to find points to attack on the target device, depending on if you want to do a voltage glitching attack or a clock glitching attack. And you want to search for signals on the device, which I'll get more into that a bit later. And you need to prepare the target for glitching. And finally, you need to set up the FPGA for performing these attacks. So when you're choosing target code, you want to choose instructions that are typically like a branching type of instruction or a security check. If you target code that's nearby computationally intense code, you might be able to make use of power traces to indicate when you're nearby that code. And you want to make sure that you have you want to target code that can be easily reached or reset when it fails. And if you're not, it's much better to target code that's not on top of an operating system of any sort. So if you can reduce the noise that is between any sort of signals you're trying to read, that's much better. So when you're reviewing the data sheets, if you're doing a voltage glitching attack, you want to check what the rated tolerances are for voltages. And you need to listen to these, especially if you're doing a spiking attack, because you could accidentally fry the target chip that you're trying to attack. And with brownout detection, oftentimes the manufacturers rate what the minimum pulse width is for the brownout duration. And this helps determine what the maximum duration is for when you're doing actual glitching attack. Of course, you also want to check to see if the device has any sort of security features and if it claims to have any. And yeah, that's not much else to say about this slide. When you're testing the target's tolerances manually, you just use simple code like this. And this is really just to verify if what the manufacturer is claiming about their brownout properties to be true. And sometimes, like in practice, when I tried to do this to the Arduino chip, it claimed 2 microseconds, but I actually ended up with 200 nanoseconds. So it was actually better than they claimed. So when you're trying to find points to attack on the on any sort of devices, depending on what you're trying to target, you're going to be looking for certain things on the board. So as an example, if you're trying to do a clock glitching attack, you should try to look for external crystals on the device and see if you can just rip those out and instead supplement your own clock signals to it. Another thing is good is decoupling capacitor. So if you're doing a clock glitching attack, you're going to have to also remove the pair of decoupling capacitors nearby the clock. Also, with decoupling capacitors, it's easier to just solder on a wire directly to the high side of the power rails if you're doing a voltage spiking attack. And if you're doing a brownout attack, you're going to want to be careful about removing the decoupling capacitors that smooth out the connection to power. Other things you could look for are voltage regulators, voltage dividers, and the power supply lines if you're really feeling adventurous. So now with signals, so what I mean by signal it's information emitted by the device, which gives you a hint about the internal executing state. And these signals can vary in terms of value quite greatly because of noise introduced during execution or just the general quality of the signal that you're choosing. The parameter that we're guessing here really is the maximum delay range. So I'm going to get more into the glitching parameters a bit later, but we want to make sure that the delay range is about as small as possible. So the signals oftentimes are used to start the delay state or close in closer to when we are trying to find when we want to start the counter for our glitching, when to emit out our glitching signal. And these signals could be any one of these. It could be a GPIO toggling, it could be status LEDs, serial messages, any of these things right here. So I'm going to go talk about this equation a bit later, but it's just a heuristic equation that was the one that worked out for me at the end of the day. So this is what I used to calculate from the timing from disassembly. And pretty much at the low end, I took the total amount of instructions I had, and at the high end, I took the amount of cycles that I had. And this was just added on, like I subtracted the pipeline size on the low end and added the pipeline size on the high end just because. It's a heuristic equation. There's not really much rhyme or reason with it. This is what worked for me. And yeah. So when we are preparing the device, depending on what we're trying to do, we're going to solder or desolder the type of glitching on it. So with clock glitching, we remove the device crystal and its nearby decoupling capacitors. And with the voltage spiking, we just can find the decoupling capacitor and solder onto the high side of it. If you, as an example for the voltage spiking attack, you can look on the Chip Whisperer Lights tutorial, which does exactly this. It goes on the highest, it has you solder a wire to the high side of the cap, of a power cap, and lets you do voltage glitching like that. If you're doing a brownout attack on a device, it's best if you either just remove the device altogether, or if you find the voltage regulator directly connecting to it, and then just remove out any sort of decoupling capacitors. So this is the, oh, you guys can't really read that. So pretty much like this is what I ended up trying to create as a gigantic state machine for the glitching device. I can't really read it that well from here, but starting all the way at the top, we wait for some sort of initializing signal of when to send out our test case, if we have any. And then from there, we either wait for some signal or just go through a raw timing window after this test signal is sent out. And then we emit out our glitch. And from after there, well, right here, like after there, then we try to either wait for a sample or we restart the device and try again. So the parameters that we're trying to get at are the glitch duration, which is the amount of time that we send our glitch signal out to. And the glitch signal could be anything from our clock glitch signal, or the amount of time we brown out the device, or the power supply to the device. The delay length is the widest length that we have, and this is when this is the period from when we wait to send out our glitching signal. Now, another thing you also have to consider is that these types of attacks don't always work the first time when you try it. So you oftentimes have to end up just trying it over and over again, over a tight range. And so this is a type, I generalized the FPGA components that I used on the device. And they consist of three different components. One is the glitching device, which is something that generally did not change too much. And this was the actual device that sent out the glitching signal and took in the signals from the test case and the sampling device. So the test case device is the one that actually sends out a test case to the target device, and this could also just monitor for when to start the delay phase of when we put a counter to send out the glitch signal out. And the sampling device is the one that checks for if our glitch is actually successful or not. This is a piece of code that should be at the highest precedence because of just the nature of the FPGA and the Verilog used and that stuff. So anyway, the tools I used was a DE0 Nano device, and this FPGA did its job fairly well, considering that it didn't actually have any sort of 5-volt rails. And this is something you need to consider is what the output voltage is of the device, as well as what the maximum clock speed is for it. So on the ATmega 328, the only thing I tested both clock glitching and brownout glitching. And the code I tested was a very simple code which would toggle an LED on and off for a small duration of time in an extremely long loop. So they used two different test cases. One would blink an LED on and off for 1 millisecond, and the other one would blink it off for 1 second. And this would be in a loop that would go on forever until, and when it exited out, um, it would turn on another LED, a completely separate pin, to indicate when we're successful with our glitching attack. So this is a really rudimentary example that I used. So for the glitching attacks, I directly supplied what I was attacking to the device, and I only reset the device when it actually didn't respond back. And that helped me get more consistent results. So the signal I used for both of them was the toggling of the LED on and off. So that was the main test case that I observed to send out my delay ranges to. So something that then I went on to go test the threshold, which I mentioned this before, so I'll just go by that real fast. So this is the instruction counting from before, and this is the range of, this is when I got this is when I was able to tighten the range used for the delay on the glitching device. And this heuristic equation is the one that just worked for me in my examples. There's not really any science to it. It was just what worked. I initially tried to count the cycles to the between and the disassembly, referring between that and the data sheet, and that didn't quite work for some reason. I actually got a smaller value for the delay when to send out the glitch signal. And this is an example of my clock glitch setup, which isn't quite complete because right here, this is the logic converter. There was an additional wire connecting out from here to here, which is the LED that blinks on when the glitch is successful. So for my clock glitching, I use a duration of 60 to 80 nanoseconds for the glitch pulse. And I use both a direct XOR and a three-phase XOR successfully against the device. The delays for it, however, were fairly consistent. As in, whenever I performed the actual attack on the device versus the two examples, it actually came out to be pretty much the same value in terms of the delay value found. And the value was actually smaller than expected. So this is a non-fully connected voltage glitching setup. And the thing that's nice about the 328P is that you just power it off 3.3 volt rails. And this really helped me save a lot of time when I needed to perform this experiment. So with this, I performed brownout glitching, and the delays were fairly similar, but the durations always varied whenever I got a successful glitch out. And it took more tries. It took a longer time to work than the clock glitching, which would work within a matter of seconds. This one might take a few cycles and some resets in order for it to work. So this is just me going over what I used for the FPGA parts sections. For the glitching device, it was a direct XOR and a three-phase. And not much else to say about this. So problems I encountered were issues with your standard issues with your FPGA IDEs, the logic translation between the ATmega and the FPGA, standard analog problems, and when I tried to do the transistor switch for the brownout type of glitching on like a 5-volt example, I encountered problems with having the delay introduced from the transistor switch. So this is another example. This is the the LPC 1343. Um, this is a development board from a programmable logic training class, and this is meant to be used as a timing attack example, which communicates out over serial asking for a password. And I decided to use this probably in very poor judgment as a pure black box attempt to see if it were really plausible to try to do this completely black box. So simply, I would monitor I would send out a test case to the device with 17 A's. Where is that? With 17 A's, and then I would monitor back for incorrect example message for the I in the message sent back. This required me to build additional logic or take additional logic to do some serial parsing and that stuff. In practice, the signal itself had very large ranges, so this turned out to also be a very poor quality signal to use to gain insight to what was being executed within the device. So moving on, like when I prepared the board, I ended up removing the crystal on the board with a bit of heat and some mechanical force. And I also removed the decoupling capacitors, as you can see right here, kind of. Yeah, so once again, this is what I used. Oh, that's mistitled actually, but yeah, so in conclusion with this one, I actually was not successful with attacking this. And I suspect the reason being why is because this was constructed as a timing attack type of exercise. So there may have been like multiple comparisons being done against the each character within the passcode, which would then have a delay introduced per comparison. And what this basically surmounted to was having multiple checks on every single character being done. So the moral of the story here is if you don't have a dump or any sort of disassembly of what you're targeting, you're going to have a bad time. All right, well, how much time am I? All right, so I'm going to now talk about the things I wanted to try out, but I didn't have quite enough time to. So this is a door lock example. So right here at the top is an emergency power jack. And I thought maybe this would be kind of neat if I could get a glitching exploit working on it. Unfortunately, there is this little capacitor right here, which actually kind of stopped me from really getting successful with it, given if I pried off the doorknob like I had done so, if I were to try to do a glitching attack on it, it wouldn't really have much point because this thing right here is the connector to the motor that drives the doorknob. So there wasn't really much of a point to do this example. And even if I did get a successful glitching attack off on it, it would be fairly difficult to build a rig in order to perform an attack on the doorknob. And this is the Intel Galileo. I wanted to do a test on this one to see what it'd be like to try to glitch out a CISC architecture device. This one would probably be done using a voltage glitching attack. But I wanted to point out the crystal right here, which I believe this is a 250 megahertz crystal. And the moral of the story here is that you are pretty much going to be limited by what your hardware can do when you're trying to do these types of attacks. So, and finally, we have this set-top box, which I was way more than a little ambitious when I tried to really poke at this thing. So, just as an example enumeration, we have our external crystal right here on this unknown die, which would have definitely complicated things. And over right here, we have a voltage regulator, which may or may not be wise to attack on this thing, seeing as it draws about 200 milliamps from what I measured. Now, we could also look at the underside and learn a bit about where these decoupling capacitors would be located. And in practice, or what I was told from a lot of people, was that these decoupling capacitors are typically directly underneath the device that you're trying to help shield to, to help avoid any sort of extra jitter, which is effectively what you're trying to introduce to the targeted device. So yeah, if you're looking for any sort of like decoupling capacitors on a BGA package type form, such as this unknown device, usually you could just look directly under it and you'll find the decoupling capacitors right there. So experiments for the future. I really wanted to do a glitching attack on a device that had a frequency multiplier. I just wanted to see how that would end up working out. Attacking devices which claim to have some sort of mitigations against it. Also, combining multiple types of glitching attacks. I'm not sure if I put this paper inside the citations, but somebody actually tried to use a glitching attack by somebody tried to implement their clock glitching attack by having the device on a hot plate, which actually helped them out when they're trying to do their clock glitching attack, which is pretty interesting. Want to know what it's like to attack memory devices and how plausible it would be to attack some code that's running on top of an operating system. So if you're on the defense side, you should try to look for devices which have these things, which are glitch detectors, a good brownout detection, lockstep cores performing checks on one another, asynchronous internal clocks with dummy cycles, devices with internal oscillators, because if they have an internal oscillator, you can't really clock glitch it. A halt on invalid instruction execution, which actually would mitigate against or make an attacker's life pretty difficult to successfully get a glitching attack off. And then finally, you should also just not have any unnecessary diagnostic signals on your device, which give attackers hints to what code is being executed within the device. So if you're a vendor, you want to search for these ICs, and you also should definitely try to test against it. If you write code to defend against these types of attacks, at the end of the day, you're really just going to be buying time if your devices are vulnerable to glitching attacks. So here's the conclusions. So glitching attacks are cheap, but they vary greatly in implementation. When performing a glitching attack, multiple tries are often required. And if you're a vendor, you should try before you buy. So yeah, this is what I have. And these are probably not even a piece of the materials I suggest to read. All right, so any questions?
You mentioned chipset for life.
Oh yeah, so I totally, by the time I wanted to use this device, actually, but I was already like so used to using the D0 Nano for my FPGA stuff. You could totally use it. I'd imagine there's definitely a.
You haven't looked at it or tried it?
Oh no, I have one,
Okay.
but like I tried to use it a little bit. Yeah. So like my tool chain was already like by the time I got it, like yeah, it was already like that by then. I wanted to use it a bit more though. Yeah.
Is the glitching code available for the D0?
No, I will post it, and those are famous last words of many people. Back there?
So I see that, so here you presented you programming an FPGA and also the other one was also an FPGA yourself, and then you try to glitch it, or you also glitch some actual system?
I mean, I really wanted to move on to glitching like a full-blown system. Ultimately, I didn't end up getting enough time to try to do so. And besides that, I would have to like deal with the whole responsible disclosure process to do so. Yeah, I really wanted to do that. Ugh. Okay, any other questions?
If you're taking out all the decoupling caps in a full-blown system, I would think that would be really,
Yeah, it's pretty dangerous. You want to take it around the thing you're targeting, though. That's the general idea of it. You definitely don't want to take it. You don't want to take the decoupling caps out near the crystal if you're just doing a brownout attack. But like any of the power decoupling caps near the thing you're targeting, you should try to take those out. But yeah, you want to do that slowly because it's yeah. All right, any other questions?
you're taking out the decoupling caps that you have like issues with, like, you're just sorting out the decoupling caps versus short.
Are you talking about shorting the decoupling caps out?
Is that how you mean you're sorting the ground from the high side?
So I tried doing some experiment like that on a device, and it wasn't quite successful in terms of doing that. Not really sure why it didn't work, to be honest with you. In terms of like doing a live attack is what you're trying to say, right? To like short the power caps out. I just think that it's just the circuit wasn't made like that. It's definitely a lot easier to target a voltage regulator supplying the juice to it because there might be like it might be like connected to multiple lines depending on the device that you have.
What would be your dream tool to make your job easier as a glitcher?
Dream tool. Guess like something with like actual magic inside of it. That'd be my dream tool. All right. Yeah, I don't know the answer to that. That's why I give that answer. Any other questions, guys? All right. Well, thank you.